Transverse problem seminar, and Bill Meinhardt is speaking this week. So
on histotomography, right? So, okay, so you haven't heard this word before because I just made it up. I hope you'll find it entertaining. So somehow the idea is usually in tomography we take a line integral. This is a line integral. We start from x and we go in the direction xi, unit vector, x plus t xi dt. We get a line integral. So loads of interesting tomography problems involve a line integral. And so the idea is that in some types of measurement, rather than knowing just knowing the integral, the average value along the line, we actually know the distribution of values along the line. So what I mean is, our line hits voxels and finds some number in them. So rather than just adding them up, we know how many of each value it hits along the line. That's actually what I mean. Right, so the distribution. You don't know what order they come in, right? You just know how many of each value. So think of the histogram along that line. One way of thinking of that is that if you have some particular value for the answer y, we need to know how many values of t satisfy f along that line is less than y. And of course, if it's not discrete, that's actually the measure of the set of t that satisfy that. In other words, it will be a bunch of intervals, and we add up their lengths, and that's the measure of that interval. So this is very familiar from probability. So we kind of think of the idea of a cumulative distribution of how many there are less than a certain value, and I'll call that capital phi. And the distribution, so we just think of the usual hump-shaped distribution of how many in each bin between certain values, that would be the derivative of the cumulative distribution. And so this is very familiar from probability. You know, you have a cumulative distribution and a distribution. But I'm doing it just for values. They're not probabilities, but we can use the same idea. So you can either know the cumulative distribution, everything less than, or effectively this tells you everything between two values, right? So for any two values. So that's what I mean by distribution. And in the discrete setting, of course, if I put it into bins, that would be a histogram, and we're thinking of a histogram per line. So just to kind of fix these ideas, so here's a curve, it doesn't matter what it is, but you know that will be t, and this is x for t xi, something like this. The distribution of values looks something like this. In other words, the point is, what am I trying to say? So you get a jump where you have critical points. That's all. So this is, I just put this graph on its side so we could compare it with that. So you look at it this way, that's the distribution, and this is a cumulative distribution, right? In other words, you just add up that from one end. Yeah? So it's typically what a distribution looks like. Usually in probability we just have positive, non-negative functions, but I'm going to allow ones that go negative. So the histotomography transform, all I mean is you get the distribution, well I could have defined the cumulative distribution, right, of a function f as a function of which line you go along, and that's the data for the histotomography transform. So first of all, just if you just had a one variable function, so the function is of t, say, then so think of the mean actually, because you know that from probability. If you integrate the function, assuming that exists, it's the same as taking what you might call the first moment. So you multiply by the value times how many you have of that value, and that gives you the sum. That's kind of obvious, isn't it? It's how you work out the expected value from probability distribution. Okay. So that means that if we have the histogram data, if we have the distribution, we also know the integral. So it means we know more data if we have the histogram, and we'll come to physical situations in which you might know that data in a minute. So Right, so that's the first moment. And we can define the kth moment in a similar way. You're familiar with the second moment as being the variance, if the mean was 0 at least. So you multiply by the difference to the mean squared and integrate the distribution, get the variance. And so the point is that if you want the integral of the kth power, you take the kth moment of the distribution. And actually, that's kind of easy to prove for f positive or non-negative, but in this paper, which we'll mention later, it shows you it does actually work for functions that contain negative values as well, which is kind of interesting. So just to think, so suppose you have the distribution rather than the value. We know the integral, so we know the Radon transform. So here's the kind of fun thing: you can take any number of moments. Well, I don't recommend taking the 100th moment. That's probably just rubbish, right? Because raising small numbers to the power of 100, you get pretty much zilch. So but up to 3 and 4, you get reasonable values for the moments, and so obviously what you get is the Radon transform of the power of the function. You say, so what? That doesn't really help me. I mean, I've already got the function. I do the inverse Radon transform from the mean. I mean, what else is to do? Why would I want to reconstruct f squared using the inverse Radon transform? From these moments that are inherently less accurate, and quite right, it doesn't seem to achieve anything, except that it's kind of fun. Well, that's a short talk then, isn't it? It's kind of useless, right? So it's kind of, you might think that having that whole histogram gives you loads more data. The interesting is, it does. It gives you the same data over and over again. I mean, you just Radon transform for each moment, the inverse Radon transform for each moment, and gives you the function you want to some power, and then you kth root it, and you've got another picture of the same thing. It doesn't really achieve anything except having more data. Okay, I mean that's good because it averages over error, but okay, so I just said that. This is kind of, we can have the kth moment, and the histogram transform is the Radon transform of the kth power. And it probably does, it's kind of interesting maybe if the function's negative somewhere. Yes, that's my first result. It's entirely trivial and perhaps a little pointless, but it shows you don't kind of really have any kind of particularly different data in a way. So I just said that. It shows to say a non-negative function is determined completely by its moments. And so obviously if you have the histogram data, the distribution, you can calculate the moments. But for reasonable functions, if you know all the moments, you know the histogram data. Because that's the classic or inverse problem of finding a function for its moments. Right? So that's kind of interesting because you can look at this histogram data either way. You can say we've got bins of different values, or we've got moments. And essentially they're the same data, but I've just given you quite an amusing way to deal with the moments. And the question is maybe, can we do something with the bins that's a bit different? Also, I guess it's actually kind of interesting that all I have to do is an inverse Radon transform, which is linear, which is nice on the moment. So I calculate moments, that's easy. Inverse Radon transform, and I have to do something a little bit non-linear, but it's only kth roots of each voxel, So it's a non-linear inverse problem, but it's very kind of easy. Whereas, think about, you've got this histogram data, and you just try to fit everything in your histogram, not just the mean. Well, that's kind of non-linear, but counting how many things, how many values occur, is not a linear operation. So you can't add histograms, can you? In that way. So. Right, so now what you can do with bins. I want to consider the sub-level set. I think it's time for a picture. Right, so here's a hill. This is our image. In other words, that's x and y, and the height is the value of the image. Right? And these are contours, like on a hill, also called level sets. So in other words, I think we use x1. Yeah. I mean, x1 and x2 would be more intelligent, because then I can call this y, which is the notation I use, the values of it. So here are all the level set, the values that have the value y, and the sub-level set would be everything below that altitude on my hill. Right? So a level set is a contour, a sub-level set is everything below that contour. Which is, you know, I wish my GPS had that function, because then I could avoid driving above a certain altitude and not get stuck in the snow. In Derbyshire, that's an issue. You get to know these things in Derbyshire. Okay, so the sub-level set is all the x's in Rn, and it's 2 or 3 really, for which f of x is less than or equal to y. And then the characteristic function of that set is just the function that's 1 where it's less than or equal to y and 0 otherwise. Right? So in other words, you know, looking down on that, if that was my contour, then the sub-level set for that contour would be everything else. I mean, up to some, you know, probably have some domain of interest. So here's my second kind of neat observation. That you see, if you take the Radon transform of the sub-level set, that's just a cumulative distribution. So let me kind of draw that. So here we have a line, right? And my characteristic function is just 1 here and 0 here. Right? So the Radon transform just measures how much of the line is in the 1. Right? That's what the Radon transform the characteristic function does. And that is just the measure of all the values of t along the line of less than y. Is that okay? So Radon transforming this characteristic function just kind of masked in a way that you think of, you know, tomography just masked off the values that are less than this contour. Radon transform that as a function, it's the same as just, well, up to a scale, just measuring the length, right? So the cumulative distribution is the same as the Radon transform of the sub-level set. So again, we can do that, right? So you give me the cumulative distribution, or you give me the distribution, I just integrate it, and I get the cumulative distribution. And then I take value up to a certain level, and I inverse Radon transform that, so it just goes Radon transform data, and it gives me a picture of the sub-level set. If you want to think of doing a bin of a histogram, so we've taken it into bins between certain values, then if we inverse Radon transform that, of course, we just give me the difference between two values. In other words, a fat contour. You know, so you've got a histogram which is actually bins, discrete bins of certain ranges of values of y. And you know, in practice, you inverse Radon transform, it gives you a contour. And that's kind of quite neat, really, because, again, I made it into a linear problem, just do an inverse Radon transform. And then you get contours. And I think that's kind of fun. It's kind of a completely different way of doing it, and it still just uses a Radon transform. So what's this good for? And, well, there's actually a lot of problems where you get histogram data. There's something quite physical that distinguishes them, that maybe I can articulate, that a lot of problems, you have something going through a long array, and it goes through a bit, and then it goes on to the next bit, and something else happens to it. But the input from the previous part is, the output from the previous part is the input to the next bit. I mean, it's kind of cumulative effect, and that's why you get an integral. So, for example, if you have a transport equation, which is a differential equation that says, how many photons, get to the next voxel, and you lose some by attenuation, then that's why we get an integral along the line. But there's some other problems where stuff's kind of affected separately in some different variable, and spectral problems are a good example of that. So, infrared chemical species tomography, we put in a whole bunch of different wavelengths of infrared light. And the idea is that they have some absorption spectrum. Well, so I guess this is the wavelength, and it's kind of absorbed in this. So say water absorbs in this band. That's the idea. And so when you put in light at that frequency, you kind of just get the amount of water in the path. That's kind of pretty much it. But the thing that's kind of more interesting is that some other physical properties, like pressure and temperature, would shift this band, and so you could take this as an indication of temperature. So suppose you wanted to image at temperature and you had a uniform distribution of water molecules, then let's just turn this round so it's a peak. That's a peak at one temperature, that's a peak at another temperature. That's a picture of me having 3 temperatures that I went through, right? And now I've got more of the voxels have, twice as many voxels have that temperature. It's just a histogram, right? I mean, up to the fact that this isn't exactly a delta function, you know, but it's all kind of binned. So basically, if you translate the wavelength as a monotonic function of temperature, in a certain range at least, then you can interpret that spectral data as a histogram. So that's an example of chemical species tomography, which is why I first started thinking about this, which was a workshop we organised in the Mirren programme, and Hugh McCann organised it, and a lot of people who fire infrared laser beams through combustion chambers and other kind of chemical reactions and do spectral tomography. But you know, it's not just infrared light. Obviously, it's anything that you can do a spectral measurement, you might get this kind of phenomenon. And you know, the interesting thing about these chemical species tomography people was they were thinking, well, I've got so much data for each line. Do I really need to measure so many lines? That was kind of their point. And I went to a very interesting talk. It was very interesting because it was wrong, where somebody said, well, because I've got a whole function for each line, could I do the whole tomography with just 2 parallel beams? You know, I mean, if you count the amount of data, it sounds quite plausible. It's really interestingly wrong, because there are kind of checkerboard patterns of rearranging things that will get exactly the same data for 2 different configurations. So no, you exactly can't do it with 2 perpendicular parallel beams. But you know, my question was, surely there is more data in there, and I've just answered that question. I've said exactly, you know, for each moment you get exactly the same picture, and for each bin in the histogram you get exactly a fat contour. And that's exactly what the information on the data is. But they wanted to use incomplete data, mainly because it's pretty tedious getting a bunch of lasers from every direction through your, you know, pressurized steel vessel. I mean, I had to make a little window in it or something. It was actually really inconvenient. So they wanted to know what you could do with less data. And so that's kind of, immediately we have anything we know about limited data Radon transforms we can now use in some way. So there's a bunch of results, and so for example, you might have limited projections, so you can't project, we have a full projection but just not from so many angles. Or you might have lots of projections but your sensor's too narrow for the whole field of view that you want. And those are 2 interesting cases that have algorithms that you can do something with. So for example, there's a whole class of microlocal methods which actually, if you went to a talk a while ago by Sean, was an introduction to microlocal things for Radon transform. The point is that you can quite often get the singular support, in other words, where the jump or spike changes are in the picture, from a relatively crude method, and sometimes you can do that with less data. So the point is, in my sub-level set, the level set is the only place anything's jumping. And so you'd exactly get that from a technique like lambda tomography. Because that just recovers, it doesn't give you the smooth part, it just gives you the jump part, roughly. So you know, that would work fine. So you could do all kinds of hokey things like lambda tomography for each bin, or for each sub-level set. Okay, so that was interesting. And then there's limited data things, limited sensor things like the 2-step Hilbert transform method. Which gets a good reconstruction everywhere that's completely illuminated. So in other words, every point where you get rays from every direction, like the middle, that's in the sensor view, you can reconstruct correctly. And the bits where you only illuminate from some directions, you can't necessarily reconstruct it. And so you can actually apply that to each sub-level set, then, I mean, you could do, what's the opposite of super level set? I don't know what it's called. You know, or just the level set itself that's a bit fat. You could use these methods And you know, so some contours you get because they were in the field of view that you had complete illumination, and some you wouldn't. But you know, that's still a win, isn't it? We've got some contours of the picture, and some contours kind of incomplete because we don't know bits of them. Well, we can probably just smooth them over and fit something, right? So same with this. If we, with lambda tomography type methods, it's still, if you don't have enough directions, then you can't find things that are tangent to those directions. It's a kind of obvious law of tomography that if you want to see something change, you have to fire some rays that hit it and some that miss it, and then you can see that edge, right? But the edges now are the edges of my level sets. The function is smooth, but the edge of the level set. So, you know, as long as I'm measuring in this angle, I'll get this bit. But you know, if I miss out, say, this direction, then this bit will be wrong. You know, this bit will be wrong. But you know, I still get parts of contours to fit together into a smooth function. So it's probably, you know, that does seem to be better. We've got to try this numerically. It's kind of fun. There's also a bunch of things called discrete tomography, and people say discrete tomography, they actually mean several different things. So I'm going to pick this apart. So one of them, that's kind of more practical kind of approach, is where the image consists of only a few grey levels. So it takes a few values. For example, just two values, 0 and 1. But it could be a few. So you know, basically just have a few materials in there. And there's a bunch of algorithms that address that by doing something like an algebraic reconstruction technique, but basically just knocking it back to be just the nearest of the two values that you know. So Dart is such a method. Jost Battenberg is a big player in this discrete algebraic reconstruction algorithm. And so there's not a lot of theory there, but there's some really good practical algorithms. And so my point is obviously that I could apply those to each level set, each contour, fat contour, or each sub-level set, to do it as a discrete tomography problem. And you know, so you've already got a method to do it. There's a whole bunch of results in geometric tomography. And they're mainly about convex bodies. And they come from a whole other stream of literature that's before X-ray tomography. There's more to do with, if you've got a shadow of something from every view, can you tell what the thing is? I mean, obviously if it's not convex, you're a little bit, you know, you're not going to see in the dips in it if you're only looking at shadows. But then the extension of that is that you just get the path length through it, so it's like translucent. And of course that is actually just tomography of something that is 1 or 0, but it's called geometric tomography. And there's lots of nice results for convex bodies. So in my case, if the soup level sets or the sub-level sets were convex, then you can use these methods. And the point is that you can get a convex body from just 4, actually, non-rationally related angles. So it's kind of weird that they have to be, you know, not nice angles. And it's convex, so you can, so where the sub-level sets or the soup level sets are convex, then you can definitely do it with 4 well-chosen projections. I mean, 4 not badly chosen projections. There's a whole other kind of discrete tomography that people do, and there's a different bunch of people that do it generally, where everything's discrete. In other words, the values are discrete, but the lines and the voxels are discrete. So it's basically a problem on graphs. You know, it's a fully discrete problem. And so there's a whole literature that's like tomography on graphs. So you can only fire your stuff along the edges of a graph. And these are not really used for literally tomographic imaging. They're used for optimization problems and things like scheduling. They just turn out to be tomography on a graph. So they're kind of quite popular. And mainly what people study is the complexity of the algorithms for solving them. But there's a version of this which is exactly the discrete version of histotomography, and it's called a coloured graph tomography problem, where coloured just means instead of values they have a discrete set of values, finite set of values, which can be assigned to each vertex in the graph. And then there's combinatorial ways to solve it. So it's interesting that they kind of have a different cut on histotomography in the discrete thing. But I mean, the algorithms are mainly just the complexity. Okay, so that's for the scalar story, and just a little review of that. We're looking for a scalar field, and we could do it two ways. We could either do contours, level sets, from each bin or up to a certain bin in the histogram, or we could get our distribution, we could take moments, and then just reconstruct the kth power. So there's two kind of quite distinct methods, and the second one, the moments, didn't really seem to have any leverage because the level set one seems so nice, actually. There's loads of things you can do with that. Whereas the moments just seems like you're doing the same thing several times for a different value of k. And as k gets bigger, it gets worse anyway, because you're raising small numbers to big powers and adding them up. So now contrast to vector and scalar tomography, because there are lots of cases in which you get distributional or histogram data in these cases as well. So the thing that I have in mind is the longitudinal ray transform. That's the kind of easy and obvious one. So suppose you have a vector field, think of, say, a velocity field, something like that. And for each ray, you integrate the component of the vector in the direction of the ray. So obviously, you could just integrate each component of the vector, but to make it related to the direction of the ray. And so the idea is this comes up in Doppler tomography, where you're using the velocity of some medium to Doppler shift some wave phenomena and measure the accumulation of those to measure the velocity. And the point is it only measures in the direction the wave's going. For a tensor field, say a symmetric rank 2 tensor, aka a symmetric matrix F, then we dot it with two vectors to get a scalar. Right? We multiply it on both sides with two vectors. And then we get a scalar. We integrate that along the ray. And we're thinking something usually like strain as being our archetypal tensor. And we'll see how this arises a bit later. And so we can take the histogram version, right? So instead of integrating, we take the distributions of these values, and we put histo in front of anything you know, right? So histo LRT or whatever. Okay. So the longitudinal ray transform turns out to be quite a tricky beast, even though it's the simplest to define. And that's because it has a null space. So the point is, if you just do velocity, it turns out that if your velocity field was a gradient of a potential, of a scalar potential, you get exactly zilch from doing this measurement. Basically, you have a derivative and you integrate it, you just get the boundary values. And if you're far enough away so it's 0 outside some rate, you get 0. So the LRT of a gradient gives you nothing. So it's kind of interesting. So suppose you want to find the curl of the circulation of massive ocean currents, and you've managed to get some seismic data from an oil company that incidentally got the Doppler shift when they're actually interested in the seabed, but had to go through the water. You can find the curl component, you can't find the gradient. So you want the circulation of ocean currents, you can get that, but not any potential flow. And for rank 2 tensor, the equivalent of potential is to get a vector field, differentiate it so you've got a matrix, symmetrise that, and that's what we call a potential tensor field. It's a symmetric derivative of a vector field. And the way to think of this is you have a displacement vector field in a solid. The symmetric derivative of that is called the strain. Right? That's just what the strain is. It's a symmetrised derivative. So it ignores the curly part, it ignores any kind of rotation, which is how much it's stretched and sheared, but not rotated. So in general, we can do this for any rank tensor field. We just differentiate the lower rank one and symmetrise, that's it. So it's called D in Schauer-Fujinow's book. And the nice thing is that there's a reconstruction formula for the LRT. And it's really just a kind of filtered back projection, just as you get in scalar tomography problems. It just looks rather like the inverse random transform. But, of course, it reconstructs it up to not knowing the bit that you can't know. So it reconstructs it up to a potential field, just the kind of curl part. So, okay, so So one kind of interesting question in these is, because there's this whole bit that you can't find from the integral data, and you see exactly the problem was that you integrated a derivative and that cancelled out, right? So what if you get the histogram data? Do you do any better? And you could do that, say, in Doppler Velocimetry, because you get a distribution of sound speeds. No, distribution of frequency shifts, sorry, from your Doppler measure. Okay, so there's the tantalising possibility that you can do something better with the LRT longitudinal transform. There's some other ray transforms that come up that are fun, and probably the sort of next simplest is the transverse ray transform, and this p psi just means you're going in the direction psi. Instead of projecting in the direction you're going, you project perpendicular to the direction you're going. So that just says project onto the plane perpendicular. It's kind of an obvious idea. So it's kind of the opposite, really. And then you can integrate that, but of course the answer is a vector or matrix when you integrate. So that's a neat one, because if you have, at least you have complete data, you can reconstruct it. But there's a trick in dimension 3 to doing the reconstruction that's very neat. And it corresponds to, if you do the measurements plane by plane, which is a kind of natural thing to do, all the lines in one plane, and of course you're projecting perpendicular and then averaging those. It's not kind of clear that you can do anything useful in all directions, but in the direction perpendicular to the plane, you could just dot everything with the vector perpendicular to the plane, and then that component is just the just scalar integral. So in other words, the component in the normal direction just acts like a scalar. So for the data measured in one plane, you can just do the scalar inverse random transform, and you only get one component of your tensor in the normal direction. But hell, they'll do it for 6 different, planes normal to 6 different directions, right? And you've got 6 components of a matrix, symmetric matrix, and you're done. So the neat thing about this rather complicated transverse ray transform is that plane by plane, the normal to the plane component reduces to the scalar random transform in that plane. And so anything we know about the scalar version, we can just apply to that. So you may think, well, everything we know about the scalar histo problem, we can also do the same thing. Okay, so I just said that. Okay, so Doppler Velocimetry. So it's been around for a while. I don't know to what extent people are doing this in practice, actually. Doppler Velocity Tomography, at least, to try and get the whole velocity. So the point is, the obvious way to do it is that you just get the orthogonal complement of the potential part. Right? So Helmholtz decomposition, you get the curl part, which is basically the circulation, which is often what you're interested in. But the field could also have a potential component. So the first moment gives you, so it's called the solenoidal part of velocity, and that's easy. So the other part, the potential part. So the question is, can we get that from the histogram data? Well, turns out the answer is yes. And it's kind of fun. I don't know whether it's any use, because what I was thinking of is a velocity that's purely potential. In other words, a velocity v that is d of u, where d is actually just the gradient in this case, because it's a scalar. Are you actually going to do Doppler tomography on potential flows? I don't know, actually, but if you wanted to, today is your lucky day, because I'm going to tell you that you can actually do this. And this turns out to be quite fun. So the point is that, so we're going to use moments. And it turns out that, so the second moment would be the integral of the square. But it isn't, it's the square of the component in that direction. So v dot xi is the component in the direction. V dot xi squared is, that's the square. So if you take the second moment of the histogram data in this case, you get the integral of v dot xi squared. So the fun thing about that is that so if you get a vector v and you multiply itself, instead of dotting it, you outer product. In other words, you multiply every component with every other component, you get a matrix. So every vi you multiply by vj, put it in a matrix, right? So that's a tensor, a matrix. And it turns out that this second moment, it's exactly the LRT of the rank 2 tensor, which I have written. This is means the outer product. So you just get every component of this vector times every component of this vector, and you get a symmetric matrix. So here's the point, that the second moment data is a longitudinal ray transform of the tensor square of the velocity field. Okay, and the point is that even though you get a velocity that's a potential, when you square it, it's not a potential, right? So, I mean, it might have a potential part, but it's not necessarily the symmetric derivative of some vector field. And that's where we get our advantage. So the thing is, can you get anything that you don't know already from the moment? In this case, you can, because from what I've just said. So, I mean, one way of getting the non-potential part is using a thing called sans valence tensor. So the point is, you have a symmetric tensor field, and you want to know if it's potential. And the main example of this that undergraduates learn is to do with strain. So strain is a symmetric derivative of a vector field. So it's a potential tensor. And so people who've studied elasticity say, you give me a tensor, how do I know if it's a strain? You know, so you give me a symmetric tensor, if it's actually a strain, and linear elastic strain, there should be a vector field, the displacement, for which it's a symmetric derivative. But how do we know? Well, it turns out that just like in vector calculus, something in gradient, basically, if its curl is 0, there's an equivalent kind of double curl for tensors, and it's called the St. Valent tensor. So it's a kind of curly curl. And if you want a higher tensor, you just keep curling, right? And that tells you whether it's the symmetric derivative of something lower. I gave a talk, I mentioned this St. Valent tensor in a talk in Limerick, and I said, isn't it amazing what you could get? What's it called when you made a saint? Beatified. So isn't it amazing to get beatified for an integrability condition? And so well, yeah, maybe the general case for rank K would be worth it. Okay, so it works for rank K, but the way the formula works, and of course, skew symmetric tensors can be written as lower rank tensors in a kind of obvious way. What you do is you differentiate and then you skew symmetrize. And an equivalent of the St. Valent tensor is the corner tensor. It's just that this is a rank 2 tensor. And so what you do is you differentiate and skew symmetrize. And it turns out that in this case, when the tensor we want is a product of gradients already, then a lot of the terms fall out, and we get a relatively simple thing. So the commas are differentiated. So that's the. So what I'm saying is, the formula for reconstructing the longitudinal ray transform, actually what it does is give you the St. Valent tensor, because from that you know the part that's potential, that's not potential, the solenoidal part. So it's kind of natural to work in terms of the contents. So what I'm saying is that you can just use the formula for the longitudinal ray transform for the second rank tensor, and it gives you the corner tensor, the St. Valent tensor of this thing, and that's the data that you get. So from the second moment, you get this thing that's derivatives of the thing you want. In other words, a PDE for the things that you want. And that's kind of exactly what you get from the second moment, and you can take all the higher moments, you get higher order PDEs. But you know, in this case, we can find something a little bit useful. So I'm just going to do it in 2 dimensions, because you can do a plane at a time anyway, in which case I've just got, you know, K11, K12, K22, and that's it. There's only 3 things, right? So this is my corner tensor in terms of that's u differentiate respect to 2, 3 and then squared, and that's u differentiate respect to 2, 2 and 3, 3, and that's k11. So in other words, from this second moment you can get k11, you can get k12, you can get k22 as well, which you can just permute the indices to see what that is. Is that any good? Well, it turns out it's great because from this, you can kind of see the pattern of this. It looks kind of a little bit like a determinant of something. It is actually the determinant of the adjugate matrix of all the second derivatives. So in other words, U was a scalar, U comma ij is all the second derivatives, the Hessian matrix, and the adjugate matrix of that is the matrix of so it's kind of the inverse, but without the determinant, right? Cofactor. It's a signed cofactor. Yeah, anyway. It's just the inverse without the determinant. Bunch of cofactors. Okay, so, I mean, for example, if you take the trace of that second derivative matrix, just the Laplacian, in other words, from my second moment, I know the Laplacian of the potential that I want. So all I've got to solve is Poisson's equation and I'm done. So in this velocity tomography problem, kind of pretty much done. You could only get the solenoidal part. Now if it was potential, just purely potential, as the case that I did, you get just the second moment, and the first moment doesn't have anything in at all, it's just zero, right? Because it's potential. But the second moment now has all the information that you want. It tells you what the potential is. So that's kind of neat, and compare that with the scalar case, where you could take either the histogram data directly and reconstruct level sets, or you could take the moment data, and the moment data didn't achieve anything else. I mean, it just gave you a way of reconstructing a power of a picture, pictures of the power case, so what? But in the tensor, in the vector case, the second moment already gives you everything you need. So now, if somebody's looking for potential flow fields in the ocean, I've sorted that out. I don't know anyone who's trying to do that, but I was really pleased with myself. I did this over Christmas. I was at Centre Park, so I was really pleased with myself. I thought, maybe I'm going to go to Woodhull's Oceanographic Institute and tell them about it. And then I realised, not really a lot of call for imaging potential fields in the ocean, so I'll have to think of another excuse. Now, if only we could do this for rank 2 tensors. And the reason is that rank 2 tensors are strain, and there's lots of ways to try and do strain tomography using, for example, Bragg edge neutrons. And Phil Withers and I wrote a paper that, as a little kind of side remark at the end, we said, oh, your Bragg edge tomography doesn't work. Because they're exactly trying to find a strain tensor from its longitudinal range transform, which is exactly what you can't do. And so I started to think, well, can I play the same trick? First of all, can I get histogram data from this neutron spectroscopy method? And then secondly, if I could, can I do the same trick as I've just done? You get some partial differential equation to solve to find the strain. So I need to tell you a little bit about Bragg edge. So here's what the Bragg edge spectrum looks like. So you fire neutrons through your polycrystalline material that's been strained, and each crystallographic plane and each mode produces this phenomenon called a Bragg edge, which is a very sharp transition in the amount of neutrons at that wavelength that go through. So that's what you do. And you zoom in on a nice one. I like 211 actually, that looks really clean to me. But they've looked at this one. And if you zoom in on this curve, it's actually not so sharp. So the point is, this is to do with the separation of the planes of atoms in the crystal. And if you strain it, that changes the separation. And that changes the wavelength of the Bragg edge. So if I just strain the whole thing in the direction I'm going, it just moves the Bragg edge. So the fun thing is, what if you've got lots of different strains along that direction? You get the sum of different Bragg edges in different places with different jump heights depending on how much of each strain you've got. So actually this pretty much is a cumulative distribution of strain in that direction. So this is new, no one's pointed this out before. Okay, I guess it should be tested experimentally, this actually works. So it's not exactly true. It would be true if there wasn't this stuff going on here, because, you know, when you shift it along, this part of the curve would start to pollute it and get in the way. That's why I kind of quite like these, because it depends which effects you can ignore, but in a nice clean case, that's a straight line. I mean, whereas this is some curve that I don't know. So this will come in and get in the way. And otherwise I've got a histogram. So, yeah, I mean, just a kind of cartoon of it, you get several different jumps like this, and that this slope is the same all the time, and you add them together, you don't exactly get a cumulative distribution because of these lines. But you know, if you differentiate it, then this slope is a constant, so you get a histogram plus a constant. A cumulative histogram plus a constant if you differentiate it. And then you remove the constant, and then you get a histogram. So I guess you don't see it on that zoomed in picture, that it's got these ziggy-zaggy bits because it's smooth. Right, so that actually new insight that you can get the cumulative strain histogram from drag edge data. This is new, you heard it today. But is it any good? Well, okay, so the plan was to roll out the same methodology. I was, you know, enjoying myself at Centre Parks doing these calculations, looking out the window, watching the squirrels. So you get the symmetric power, but now U is a vector and du is a matrix. You multiply them all together and symmetrize. And as ways, these won't be potential even though their components are. So you get the same finite tensor, which you can reconstruct from the histogram data. So I've got the histogram, I can get the moments, so I can do the longitudinal ray transform, and that gives me the same finite tensor of these products. But unfortunately, because it's a non-linear PDE, I mean, and I could do that trick with the aggregate matrix in the PDE, but I don't know a trick to do this yet. So what it does is each moment gives you a non-linear PDE for the displacement vector, or the strain. And you say, well, I'm not sure that I want to solve a big non-linear PDE, but you know, you could. I mean, one thing that you could do is the strain tomography as it stands actually just gives you the boundary data. So it gives you the displacements at the boundary, basically how much you've stretched it, but nothing about the interior. So one thing that has been done is use the finite element method with those boundary conditions to get the interior strain. And of course that means solving a PDE. And okay, they're slightly different. Mine's a non-linear PDE, but it doesn't depend on elastic coefficients and it doesn't depend on boundary conditions, but it's non-linear. And there's a linear PDE, but you need to know the Young's modulus and so on. Anyway, so I pointed at least the very simple thing is we could compare the two. We've got two different ways to get the same data. And mine uses a non-linear PDE, which I don't even know uniqueness for. So, okay, that's the way it's stuck out. Indulge me with one more thing. So there's a couple of different types of strain tomography. One is polycrystalline, but instead of just getting some stuff that goes straight through, you get the things that are diffracted in a certain direction around the cone. And so typically, from each crystal will give you a spot. It's polycrystalline. I mean, there's lots and lots of little crystals, randomly oriented. So you get enough of them, the spots turn into a circle. Now, if you strained it, that turns into an ellipse. You strain it differently on the path, you get sums of lots of ellipses. And the more you have a certain strain for a certain ellipse, the brighter that ellipse is. So it's some kind of distribution that you have there, right? And you'd hope that it's the histo-TRT, but it can't be, because the strain in the plane direction has 3 variables, and we only have a measurement of a plane. So it's something less than the histogram TRT. But nevertheless, the same idea. And then even more fun, if you get a single crystal, and I'm thinking of a semiconductor, then it will make a diffraction pattern from neutrons or electrons or X-rays, which is spots. corresponding to the Fourier transform of the crystal. And then you strain it, those spots move. You strain it differently along the way, the spots blur. They blur, that blurring is exactly the histogram of the distribution of the things that contribute to it. So in other words, you get the histogram of the transverse component of the strain from that type of method. So I believe this is exactly the histogram TRT, and you're actually paying attention, you realise that I've solved this. Because one case of the histogram TRT is the component normal to the plane, which reduces to the scalar case, which is the first part of my talk. So in principle, at least, we can do, say, electron strain tomography of a semiconductor. That turns out to be quite important, because the strain in the semiconductor determines its properties at the junction. And so people actually care about this. And I'll stop there. Thank you. I haven't really left much time for questions, but I'll take it if there are. I might switch off the